In our last video, I introduced the concept of an inverse trig function. And in this lesson, and in the next one, we're going to study inverse trig functions in more detail. First thing that I'd like to do is start out by remembering what the basic sine graph looks like. So the basic sine graph looks something like this. Goes up to 1, down to 0, down to -1, and then up to 0. And then, of course, this pattern repeats. I'd like to point out, though, is that this sine graph fails the horizontal line test. Now remember that the horizontal line test from earlier this year was used to tell whether a function was a one-to-one function. So if we put a horizontal line through this graph, we would see that it crosses in more than one spot. In fact, it'll end up crossing in an infinite number of spots. So this sine graph fails the horizontal line test. So does the cosine graph, and so does the tangent graph. Now, why is the horizontal line test important? Well, it's important because the horizontal line test tells us whether a function is one-to-one. Whether a function is one-to-one is important because that tells us whether the function can have an inverse. If it's not one-to-one, it doesn't have an inverse. So the regular sine, cosine, and tangent graphs show us that regular sine doesn't have an inverse, and neither does regular cosine, and neither does regular tangent. So if we want these functions to have inverses, we need to change something about the graphs in order to make them so that they're one-to-one. And so we do that here down below. This is our sine graph with a restricted domain. This is sine, but the domain is limited to -π/2 up to π/2. When we've limited the domain in that way, we see that we just have a single piece of the sine graph. But this little piece passes the horizontal line test, because a horizontal line will pass through in only one spot. And so this restricted sine graph has an inverse. Same thing with this restricted cosine graph. This restricted cosine graph has a domain from 0 to π, we can see along our x-axis. And it passes the horizontal line test. And so does this restricted tangent graph. This restricted tangent graph just has one of the curves. It doesn't have the repeating pattern going over to the left and going over to the right. So if we restrict the domains in the domain of each of the functions in this way, it can have an inverse. And so my computer is thinking, and there we go, it moved. So it's important to restrict these domains in order to make them one-to-one functions. Now, the domain of this restricted sine runs from -π/2 up to π/2, including the endpoints. So we've got -π/2 to π/2. Remember, that's in radians. The degrees would be -90 up to 90. And the range of this restricted sine is the set of all y values, which run from -1 up to 1. The domain for restricted cosine goes from 0 up to π, and its range runs from -1 up to +1. For tangent, we have a domain running between negative pi over 2 and pi over 2. Remember that this tangent graph, this is an asymptote here at negative pi over 2. So it never actually reaches, pi over 2. Never actually reaches pi over 2, and never actually reaches negative pi over 2. Because of this, we need to have a parentheses here, meaning that it doesn't actually reach those values. Then the range. So the range is all possible y values. This graph continues to go down forever and continues to go up forever. There's no limit on what y values this tangent swoop can have. And so the y values run from negative infinity to positive infinity. Now we have the graphs of each of the inverse trig functions. Inverse sine uses the symbol sine but with a -1 exponent. It means sine inverse. Sometimes you'll also see arc sine, and that means the same thing as sine inverse. Same thing for arc cosine. That's a mess. Arc cosine and arc tangent. Now, comparing these graphs, you can see it has a little bit in common with the graph that it's mimicking, or that it's the inverse of. Now, I'd like to point out, though, is something, before we go on, something with the basic sine, cosine, tangent graphs. Remember that with these trig functions, you put an angle into the function, and then it gives you a number as an output. So remember that this is an angle input for each of these. Put the angle in, it gives you a trig value coming out. Just going to put trig value, trig value, trig value as the y value, or the output. Now for these graphs, these inverses undo what the original function does. When you put an angle into this trig function, it gives you a trig value going out. If you put the trig value back in to the inverse, it will give you the angle back out. And that's true for each of these trig functions. You put the trig value in, and it will give you as an output the angle that corresponds to that trig value. Put the trig value, angle out. So what I'm going to point out next is that these trig values run from +1 to -1 along the x. Now the y's, it's not exactly clear what it goes to, but these y values run to approximately 1.57, which is pi over 2. And the y values run down to negative pi over 7, or negative pi over 2, excuse me, as well. Now compare that to the restricted sine graph. The angles run from pi over 2 to negative pi over 2 along the x, and for the inverse sine function, they run from pi over 2 to negative pi over 2 along the y-axis. And so the domain and the range is swapped. Same thing with the range and the domain between the regular function and the inverse function. And you see that for each of these as well. The angles here run from 0 up to, it should run a little above 3, because it ends up having a maximum angle output of pi. See in our restricted cosine graph, the angles run from 0 out to pi. Same sort of thing here. And with the tangent, this runs to an asymptote of pi over 2 up there, and negative pi over 2 down here. Same thing holds. So as I pointed out, the relationship between these functions and their inverses is that the, oh boy, that's a mess. So why don't I just try and type that in? It'd be a lot of writing. A little easier for you to read here. Shrink it up a little bit. The domain of the function matches the range of the inverse, and the domain of the inverse matches the range of the original function. All right. Next up, we're told to evaluate each of these functions. So we are asked, what is the sine inverse of 1/2? Now remember, with the sine inverse function, you put a trig value into it, and your output, or your answer in this case, is going to be an angle. So we want to know which angle has a sine value of 1/2. Which angle has a sine value of 1/2? Alright, so I think sine value of 1/2. A sine would be an opposite over hypotenuse. So which sort of triangle has a side length of 1 and of 2? Well, it's a 30, 60, 90 triangle. So we've got a 1, a root 3, and a 2. To have a opposite over hypotenuse being 1 over 2, we need this to be a 30-degree angle, and this to be a 60-degree angle. Let me pause the video just for a minute. So I see that a 30-degree angle is a sine of 1/2. But I also remember that if I had a 30-degree angle over in quadrant 2, and the opposite over hypotenuse would also be 1/2. Now this 30-degree angle over in quadrant 2 is generated by a 150-degree angle, like that. So these two angles, 30 and 150, have a sine value of 1/2. So which is the correct answer? Let's go back to the sine graph. The sine graph angles need to be an output between pi over 2, which is 90 degrees, and negative 90 degrees. So I look down there and I see that this 150 degrees is outside of the acceptable range of answers. So 30 degrees must be our answer. Next up, sine inverse of negative root 2 over 2. This is my y and this is my r. R is always positive, and so this y must be negative to give us the negative fraction. So we're going to have an angle somewhere down here, or down here to have a negative y. So negative root 2 over 2. Now, second thing, we don't have any triangles which have a negative root 2 for a y and a 2 for hypotenuse. But remember that negative root 2 over 2 is the same thing as 1 over root 2. If you rationalize this denominator, rationalize the denominator of this fraction, you'll end up with this expression here. So, let's erase these. We would need to have negative 1 over root 2 as our fraction. I'm going to pause the video here, and we'll pick things up in video 2.